This presentation is delivered by the Stanford Center for Professional Development.
Okay, so we're going to really start this topic of duality. Last time I think I did nothing but say a few things about it last time that were kind of incoherent, but maybe I'll make them coherent today. So what duality is about, I mean, one way to think about it is it's a way to handle, in a way, we'll see what that means in a minute, you handle the constraints actually by incorporating them into the objective. That's the basic idea. So let's see how that works. And it fits in exactly with what I was talking about last time, which had to do with this concept of irritation versus value for a function, and the idea of a hard constraint where you go from completely neutral to infinite irritation, as opposed to a soft, something like an objective. In an objective, it's just a linear irritation function or something like that. And that means the larger the function is, the more irritated you get. And the smaller it is, actually, the happier you get. So we'll see how that's going to tie into the idea of duality. All right. So first we start with a couple of definitions. We start with a problem like this. So minimize an objective, some inequality constraints, some equality constraints. We are not going to assume this is convex. And in fact, some of the most interesting applications of the material we're going to talk about now occur when this problem is not only not convex, but it's a problem known to be hard. So that's going to be some of the most interesting applications. We form the Lagrangian. And the Lagrangian is simply this. I mean, it's really kind of dumb. You take the objective, and to the objective, you add a linear combination of the constraint functions and the equality functions, right? So that's it. Now, the Lagrangian is a function of these. It's also got some other arguments. Of course, it's got x in it, but it's also got lambda and mu. And these are called the Lagrange multipliers. There's all sorts of names, dual variables. You hear all sorts of names for what these are. Actually, in specific contexts, they can be other things. They can actually literally be prices, penalty rates, and you'll hear all sorts of other names for them in other fields like economics and things like that. So they've got lots of names. We'll see some of those later, or where they got the names. Okay, and here you'd say, for example, that lambda 3 is the Lagrange multiplier or dual variable or price, I'll justify that term soon, associated with the third inequality, so fi of x less than 0. That's what lambda 3 is. And in fact, you can even sort of get a hint at what's going on here. If, for example, lambda 3 were, 6, let's say, that would mean the following. Up here, this says that if f3 is less than or equal to 0, it's perfectly okay. If it's bigger than 0, it's infinitely bad. When you replace this constraint by this charge, lambda becomes the price, or you can call it a penalty, and it basically says fi can be positive. That's not a problem now, but you're going to pay for it. And for every unit that fi is positive, you're going to pay 6 here, whatever those units are in. Now, the flip side is actually quite interesting. You actually get a subsidy for coming in under budget. Up here, as we said last time, there's absolutely no difference between fi of x, f3 of x, for example, being minus 0.001 and minus 100. Absolutely no difference. Both are feasible, and you have no right to say that you like one better than another, period. Because it's not an objective, it's a constraint. That's the semantics of a constraint. And you can wave your hands and say, oh, no, I like minus 100 because then there's a margin. If that's your feeling, then you haven't set up the problem right. Okay? So now when you convert that one constraint to this sort of thing, actually something interesting happens. When f3 is less than 0, you actually get a subsidy because it's 6 times whatever margin you have. So when you convert this constraint to a term in a Lagrangian, you actually get a subsidy for coming in under budget. And you do like f3 equals minus 100 more than you like it minus 0.001. You get a subsidy. So I'm just sort of, hinting at the ideas that we're going to see soon. Okay. Well, that's the Lagrangian. Nothing's happened so far. Then we look at the so-called dual function, or the Lagrange dual function. It's got other names, but let's look at it. So the Lagrange dual function, it's actually very, very simple. It just says minimize this Lagrangian over all x's. That's what it says. Just minimize the Lagrangian. Now actually it's very interesting because what it's really saying is this, and by the way it's a function now of these prices or dual variables. So there's all sorts of ways to interpret this. You can interpret this as sort of, I don't know, the free market approach or something like that. This is the constrained approach where you simply say by fiat fi of x has to be less than 0, hi of x has to be 0. That's this. Then you could say, well, you'd say, no, you know what, actually we're going to let fi float above 0. No problem. We'll charge you for it if the lambda i's are positive. That would be the meaning here. But if fi goes less than 0, we'll actually pay you for it. You'll be subsidized. And this is sort of the optimal cost under these sort of market prices. So all of this will become clearer as we move on with this. Now here's an interesting fact. If you look at this function as a function of lambda and nu, what kind of function is this as a function of lambda and nu for each x? It's affine. Yeah, it's linear plus that's a constant. Okay, so it's affine. And the infimum of a family of affine functions is, of course, concave. So this function g, which is something like, you can think of it as sort of like the optimal, we'll get to it later, as a function of the prices, even if the original problem, even if these things are not convex, sorry, these are not affine, that's not convex, this thing is going to be, this dual function is absolutely concave. Okay? So that's, all right. Now we get to something, I mean, this is all very simple, but it's one of those things where you get a sequence of like 12 simple things, and the right sequence of 12 simple things will lead you to a very interesting thing. So trust me, that's what we're doing here. So the first thing you observe is the following. It says that if these dual variables or prices are positive, non-negative, these are the ones associated with the inequality constraints. Then it says that g of lambda nu is less than p star. That's the optimal value of the original problem. Okay? So actually quite an important statement. Looks very complicated. It's quite profound. It says basically if you can evaluate g, this dual function, you're going to get a lower bound on the optimal value of the original problem. That's what it says. So the argument is just it's embarrassingly simple. Let's do it this way. Look at this thing and imagine x is feasible. For any feasible x, well, forget, that is whatever it is. For any feasible x, fi of x is less than or equal to 0. But if lambda I is bigger than or equal to 0, this term is less than or equal to 0. Therefore, this whole thing is less than 0. If you're feasible, hi of x is 0, and so it doesn't even matter what the sign of nu I is. This is 0. And therefore, it says that the Lagrangian is less than f0 of x for any feasible x. Now, for infeasible x's, that's false. But for feasible x's, it's absolutely true that L of x comma lambda nu is less than or equal to f0 of x. Because that's 0. That's less than or equal to 0. And by the way, note the level of the mathematics being employed here. It's quite deep. It relies on the very deep fact that the product of a non-positive number and a positive number and a non-negative number is non-positive. Oh, and also that you can add such numbers up and and you still have something less than or equal to 0. So I just want to point out, nothing has been done here. I mean, it's just embarrassingly simple. Okay. Now, if you then infimize this over x, then, well, obviously it's less than f0 of x tilde. That's true. This is true for any feasible x tilde, and there's no conclusion possible other than this. Okay? So if you can evaluate this Lagrange dual function, you get a lower bound, period. So let's look at some examples. Let's do least norm solution of linear equations. So here's now of course this is stupid. We know how to solve this problem analytically. You know how to. Doesn't even matter what the solution is. I mean, doesn't matter. We know everything there is to know about this. But just an example. See how this works. Well, the Lagrange function, the Lagrangian function, is this: 2x transpose x. That's the objective. We add nu transpose ax minus b. So here, by the way, you have to write this as ax minus b equals 0. You have to decide what h is. H is either ax minus b or sometimes b minus ax. So All that would happen there is the sign on nu would flip or something, but it wouldn't matter. So I've written it this way, ax minus b equals 0. So you get x minus x plus nu transpose times ax minus b. Now, we're going to minimize this over x. That's completely trivial because that's a convex quadratic. That's affine in x. And you just take the gradient. You get 2x plus a transpose nu equals 0. And you get, this is the optimal. That's the x that minimizes the Lagrangian here. All right? Now we take that x and we plug it back into here to get g. So when you plug this in here, that's the x that minimizes the Lagrangian, you get this. And you get some, well, first of all, let's take a look at it. Evidently, this problem, this function here is concave because that is a positive semi-definite quadratic form. Not positive definite, but positive semi-definite quadratic form. No, sorry, positive definite. Sorry, it's positive definite quadratic. It doesn't matter. All we care about is positive semi-definite quadratic form, but it happens to be positive definite. No, actually it doesn't matter in this case because I'm making no assumption about A whatsoever. Everything's true no matter what I assume about A. Okay, so this whole function, of course, is concave quadratic. Okay, so there it is, which we knew had to happen because the dual function is always concave. Now, here's what's interesting. And we've already learned something. It's not a big deal. It's not a big deal because I know how to solve this problem. But look at this. What it says is the following. If you come up with any vector nu at all, which is, I guess, the size of b, the height of b, let's call that m. You come up with any vector nu at all, and you simply evaluate this function. Then whatever number you get is a lower bound on the optimal value of this problem. Period. Now, it might look, by the way, right off the bat, like that's totally, in this case, it's totally useless. If that's a small problem, say x has 1,000 variables or something like that, this is goofy because we can just solve, we know how to solve this problem extremely efficiently, get the optimal solution. We don't need a lower bound on it. This is actually immediately useful, by the way, immediately useful in other contexts. In other contexts, you might want to solve a least norm problem like this with, let's say, 1 million variables or 10 million variables, for example. This comes up. In fact, not quite this one, but other ones would actually be nothing more. For example, if you solve an elliptic PDE, you're solving something not quite this, but very close to this. That's what you're solving, except it has 1 million variables or more. So that's actually what's happening. Now, in that case, you can't use your formula from 263, your AA transpose inverse, and then the A transpose goes on one side or the other, which I forget, but it doesn't matter. You can't use that formula when this is 1 million by million. Okay? Instead, you're going to use some iterative procedure to come up with an x that approximately satisfies this. Okay? And you're going to have to ask yourself, when should I stop? Well, you're going to stop. Here's a very good way to do it. You look at your procedure, and you find out if during the procedure, and this will generally be the case, during the procedure, some side calculation in your procedure is actually going to produce something that's going to be a candidate for this nu. Actually, it's no one's business how you come up with any vector nu that satisfies this. If you evaluate this, that number is a lower bound. So now you know when to stop. You stop when the residual here in ax minus b is close enough to 0. Okay? You evaluate this function, and that value is close to this value where you had a nu. Okay? Then you stop, and you don't stop because you're bored. You stop because you can now prove you're within, you're 1% suboptimal, for example, and no more. So, by the way, all of that was just an aside. So if you didn't understand anything I said, that's fine. That's often the case, but that was just a weird aside. Hinting that this idea of just the fact that you get a lower bound on a problem actually has fantastic practical use. And just, in fact, many, many, many practical uses. Okay. Let's look at a standard form LP. So I want to minimize C transpose X subject to AX equals B, X bigger than or equal to 0. Just standard LP. Okay. The Lagrangian is C transpose X plus, and I'm going to add a Lagrange multiplier for this. That's nu, transpose AX minus B. And then here, to put this in standard form, you really want to write it. You kind of have to write it as minus x is less than 0. And so these are the FIs over here. Okay? So if I simply form this thing, so that explains the minus sign here on the lambda. Okay? So that's your Lagrangian. Now what kind of function is the Lagrangian in x? Hey, look at that. That says linear, doesn't it? And it seems to me that that is false, I believe, is the name for something that's not true. Isn't that correct? You agree with me? The Lagrangian's not linear in X. That's ridiculous. I mean, is that affine? Ooh. Can you have a, can you make, oh, okay. It'll be done momentarily. I never said it. L is affine in X. It's affine because there's this constant term minus nu transpose B here. Okay. Now, this leads us to something. Actually, it's related to something on the homework from this week, which was, here's a very, very simple linear program. Ready for it? No constraints. How do you minimize an affine function? So how do you minimize an affine function? I think actually more than a small number of people were stumped by this because it's such a stupid question, I think. Actually, it's not a stupid question. Sorry. It's just they wanted to make it more complicated. How do you minimize an... well, let's start with how do you minimize a linear function? What's that? What's the minimum of a linear function? Just in R2. I have a linear... What's the minimum of x1 minus x3? x2. Sorry. Sorry. What is it? It's, of course, it's minus infinity. I mean, yeah, you have level curves, which are hyperplanes, and you can just go as far as you can in the direction minus c. It's minus infinity. So there's no mystery here. What's the minimum of an affine function? It's minus infinity. Okay. Oh, by the way, notice that that's a valid. So if g is minus infinity, it's cool. It's just minus infinity. And note that it is indeed a lower bound. However, it's an uninformative lower bound. Because if someone comes up to you and says, can you help me get a lower bound on this? You can just automatically, you don't even have to listen, you just say minus infinity. That works always, I mean, as you know. So the point is, though, that g is indeed a lower bound. It's just completely uninformative. Okay? All right. Now, there's one case when minimizing a linear function, when the minimum of a linear function is not minus infinity. Exactly one. What's that?
Yeah.
When the function is 0. And that's it. That's the only way. So in fact, if you minimize this over x, you will get minus infinity, period. One exception. If this linear, if c plus a transpose nu minus lambda is 0, then this whole thing goes away and you get that. So the dual function for the standard form LP is a very interesting function. So we're going to look at it very carefully. It's this. It is a function which is linear on this weird affine set. Okay? And it's minus infinity otherwise. By the way, that function is concave. Right? It's no problem. I mean, just visualize it. It's kind of weird. It would be in R2 like my drawing a line like this and saying, here are the values. 0, 1, 2, minus 1. And then now you have to visualize this. So you can make this if you want to make a graph coming up, slope this line up. Okay? And now what I want to do is everywhere off that line, the function value is minus infinity. So just make it fall off a cliff everywhere else. That function is concave. I mean, well, it has to be concave because we know that g is always concave. Okay? But I mean, you want to visualize it, that's what it looks like. So it's a weird thing. It's linear, but then off this thin affine set, it falls to minus infinity. Okay. So that's what g is. There's a question?
Let me get why L is affine and it's not linear.
Oh, okay. So actually, the question is this function, which I write this way. Now, you just have to blur your eyes because I'm asking you what kind of function of x is it. Okay? So let's look. That is a constant. That is a constant vector. Oh, well, actually, if I include the transpose here, it's a constant row vector. Therefore, this is linear in x, and I add a constant, so it's affine. That make sense? Okay. So that's the... I mean, you have to kind of blur the details of this out when someone asks you, how does this vary with x? In fact, that's kind of the point. Okay. Now, this is really interesting. We can actually say what the lower bound property is. So the lower bound is this. If this function is the dual function, it is always a lower bound on that LP. Now, of course, if you randomly pick lambda and nu, you're going to get minus infinity here, period. Just minus infinity. Okay? In which case, it's still a valid lower bound. It's just a completely uninformative lower bound. It's the lower bound that works for all problems. It's the universal lower bound. All right. But in fact, what we're going to do is this. it says, if I pick A transpose nu, suppose I pick lambda, sorry, such that A transpose nu plus C is positive. Suppose I do that, is non-negative. Then I simply let lambda equal this thing, and then with that choice, this is true, and then I get the following. I get P star is bigger than minus B transpose nu, provided A transpose nu plus C is bigger than or equal to 0. So let's see what we've shown. And by the way, I want to point out absolutely nothing here used anything deep at all. Nothing deep. I mean, just the most elementary arguments involving like products of positive numbers and things like that. I mean, the most elementary arguments. So let's see what we've come up with. It says the following. If you have this linear program here, and someone says, what is the optimal value of it? Well, it depends on the context. If a person has a specific A, B, and C, and actually just wants to know, solve my problem, you can run some code and solve the problem if it's not too big, and if that's what they're interested in. Okay? However, you can make a very general statement. You can say the following. If you find any vector nu by any means, doesn't matter how you find it, it's no one's business how you found such a nu. If you find a vector nu such that A transpose nu plus C is a non-negative vector, then you evaluate minus B transpose nu. That's a lower bound on this LP, period. Okay? And that's not, I mean, well, it strings together 3 or 4 totally obvious things, but I think you come up with something that's not obvious. Okay? Let's do equality constrained norm minimization. So here you minimize the norm of x subject to ax equals b. By the way, we've seen that problem. In fact, I guess we just did that problem 2 examples ago. Not quite. We did the case where this was norm squared and where this was the 2 norm. Okay? Now completely general. Well, the Lagrangian is the infimum of norm x minus, and then some horrible thing here, which is affine. And here we have to be able to minimize norm x minus nu transpose ax. This is a constant, so it's totally irrelevant. And you have to be able to do that. Now this goes back to the idea of a dual norm, and let me go to that. So let's look at that. If I want to minimize, say, this, there, of this thing. The question is, what is this? What do you get here, right? And the answer is actually pretty simple. Comes straight from dual norms. In fact, we could do it for the 2 norm first, just as a warm-up. So for the 2 norm, you'd say, well, look, if norm y here is bigger than 1 in 2 norm, then I could align x with it in that direction, and then this, actually, in that case, this thing sort of overpowers. It has enough gain to overpower this one, and I can make it go to minus infinity. Okay? Now, on the other hand, if norm y is less than or equal to 1, Cauchy-Schwarz tells me that this thing is less than that, and therefore this whole thing is bigger than or equal to 0. So I could never, ever make this thing negative. On the other hand, by choosing x equals 0, I can make it 0. So that's clearly the optimal. So this is equal to, and this, this generalizes now to a general norm. It's either equal to minus infinity if the dual norm of y is bigger than 1, or it's 0 otherwise. Okay? And in fact, that's literally the dual norm. You can, it's from the definition of the dual norm. Okay? So this is what you get. All right. So applying this up here gives us exactly this. This is our y, and here you have it. So once again, this dual function is not totally obvious. It's not an obvious thing. It's something. It's linear. It's a linear function, but it's got a weird domain. In this case, it's the set of points nu where the dual norm of A transpose nu is less than or equal to 1. Okay, that's that. Okay, and then you can go through the argument here, and I won't go through it. But actually, now you got something really totally non-obvious. It basically says, if you can come up with a vector nu for which A transpose nu is less than or equal to 1 in dual norm, then B transpose nu is a lower bound on the optimal value of this problem. Here's an example. Here, ready for a dual feasible point? Nu equals 0. Well, let's check. That's 0. 0 is definitely less than 1. And now we have a drum roll to find out what lower bound we've come up with. The lower bound is 0. And that's actually not particularly interesting here because the objective is 0. Okay? So that's what it says here. Okay? So, okay. So this gives you a parametrized dual. A parametrized lower bound. It's parametrized by nu. Okay. Now we're going to look at a problem. Actually, we'll see it a whole bunch of times. It's actually just as it's sort of a simple example. It's a perfectly good working example of a hard problem. Just hard combinatorial problem. It's two-way partitioning. It's embarrassingly simple. It goes like this. I want to minimize a quadratic form. It doesn't. I don't say anything about its. I mean, W is symmetric, obviously. I can assume that, but it's not positive semi-definite. It wouldn't matter if it were. It doesn't matter. So that's I want to minimize this quadratic form, subject to xi squared equals 1. Now this means xi is plus or minus 1. Okay. And let me just first say a little bit about this problem. We're going to see it a lot, and just so you get a rough idea of what it means. So xi is plus 0, xi is plus minus 1. So we can really think of this as the following: is you have a set of points, like endpoints, and what you want to do is you're going to partition them into two groups. Okay, that's like one group, and then the other group will be this. Okay, and we encode that by saying here's where xi is plus 1, and here's where xi equals minus 1. So that's our. So we're going to use the vector here, the variable, which is xi, which is this plus minus 1 vector, to basically encode a partition. It's a partition. It's just it's a numeric data structure. I mean, it's sort of numeric to encode a partition. Okay. All right. Then let's look at what the objective is. The objective is sum xi xj wij, and let's just see what it is. So you sum over all pairs. If xi and xj are in the same partition, what is xi xj? 1. Okay? And then you add this to this thing. Now this is something we want to minimize. Okay? Now if xi and xj are in opposite partitions, this is negative. So I think that means that wij is not, hopefully I'll get this right. Wij is a measure of how much I hates j. Did I do that right? I believe so. Because if W is very high, it means that if xi and xj have the same sign, you're going to be assessed a big charge in the cost. On the other hand, if xi is high, and they're in opposite things, you're going to decrement the cost a lot, and happiness is going to go up. Okay? So wij is basically how much I annoys j, but it's symmetric, so it's some average. It's the average actually of how much I annoys j and j annoys I. Okay? Now if wi is small, it means they don't care much. So in fact this now makes perfect sense. As you have a group of people, you have a social network or something like that, and you want to partition it. I mean, if everybody likes everybody, can we do that? Yeah. Can you stick them all? No, can you? Otherwise, sorry. Which is the one? There's one that's trivial here. But anyway, I won't. There'd be obvious ones. If the sign pattern in W were such that like everybody liked everybody except one, then it would be very simple. You just isolate that one node and everything. But in general, actually finding the solution to this problem is extremely. I mean, it basically is extremely hard. You can't do it. It's so if this is 100 or a couple hundred, you can't do it. Just cannot be done. Okay. So that's the partitioning problem, and it's sort of, for us, it's going to be a canonical example of a hard problem. By the way, there are instances of it which are easy. I just mentioned, when there's some obvious solution, but I'm talking about the general case here. Okay, now, all right. Oh, by the way, it comes up in tons and tons of other. I mean, this is actually. I mean, my interpretation was sort of a joke. But the point is, it comes up in tons and tons of real applications. I mean, which are quite real. I mean, in circuit, it comes up in partitioning. It comes up in statistics. I mean, just everywhere. So, my interpretation was a joke, but it's a very real problem with real applications. Okay. Now, the dual function is this: we simply take x transpose w x. We add, as the Lagrangian tells us to, a linear combination of these functions. I write them as xi squared minus 1, so I get this. And I have to calculate, this is the Lagrangian, and the Lagrangian is quadratic. Okay? It's a quadratic function. It's right here. It's w plus diag of nu. By the way, I make no assumption whatsoever on whether w is positive, semi-definite, nothing. And now, a few minutes ago we had a discussion about how do you minimize a linear function. Now we can have a very short discussion about how do you minimize a quadratic function. And the first thing you do is let's talk about how do you minimize a quadratic form. So what is the minimum of a quadratic form? What is it?
Negative infinity.
It can be negative infinity. I agree. When would it not be?
When infinity is positive. Yep.
Yeah, when the matrix, look, if the quadratic form is positive semi-definite, then the only values it takes on are non-negative, so it couldn't be minus infinity then. So that's exactly the condition. The minimum of a quadratic function, quadratic form, is minus infinity if that matrix is not positive semi-definite. So if it has one negative eigenvalue, the minimum is minus infinity. Okay? Otherwise, if it's positive semi-definite, the minimum is 0, period. Because it can't be any lower than 0, and it can be 0 by plugging in 0. Okay. Now, if you ask, what's the minimum of a quadratic function? That's a quadratic form plus a linear function. It's a little more subtle, and there are some horrible corner cases at the boundary. But let's deal with some of these things. And you can at least answer some of it. The minimum of a quadratic function, if the quadratic part, it's complicated in general. Well, let's see, here we're just doing a quadratic in x. Oh, great. So we don't have the more complicated case. Sorry, I thought there was an affine term. So scratch everything I said. We'll come to it eventually, and it won't be fun when we do. It won't be that bad. But anyway, all right, so this is good. The simple case works here. So this is really simple. If this matrix W plus diag of nu is positive semi-definite, then the optimal x here is 0, and you just get this. Okay? So it turns out that the feasible, this is called dual feasible, that's when g is bigger than minus infinity, is actually given by this. That's a linear matrix inequality in nu. It's a very famous one. Right? It's the set, that's a linear matrix, in nu, that's a linear matrix inequality. It describes a convex set. Okay? And let's review what it says. It says the following. It says that if you want to partition a group of 300 nodes optimally, there's, by the way, no way to do this kind of global. I mean, there is ways to do it globally, but they'll just run forever and not get very far. Maybe. So you let, everybody writes their own partitioner or whatever, and somebody partitions it and then says, here's my partition, and someone else has another partition, and so on. And so you get the best of all the partitions that have been proposed, and then you want to know, how far are you from the best? That's the question. And at least one way to at least partially answer that question is as follows. If you can come up with some numbers nu, and it's absolutely no one's business how you came up with them. No one's business. If you can calculate some numbers nu, verify that w plus diag of nu is bigger than or equal to 0, period. That's all you have to verify. Then negative sum of the nu's is a lower bound on this thing. Okay? So that's all we know so far. And this is not obvious. This is not in any way obvious, although I repeat, it uses the most elementary mathematics to get there. I mean, here we use the fact that minimum of a quadratic form is minus infinity unless it's positive semi-definite, in which case it's 0. I'll skip this for now. Anyway, you'll read about this. So this is already quite interesting, that you can get a lower bound. In fact, it kind of makes you want to do something like get the best lower bound. And we'll get to that, but it's a semi-definite program. And then you can already see how semi-definite, once you see that, you realize why there's a strong connection between semi-definite programming, for example, and combinatorial optimization, because this is a combinatorial optimization problem. That's what this is. Yeah?
Does it tell us what actual optimal x is?
No, absolutely not. It's a lower bound. Now, what I haven't said is whether the lower bound is sharp or not yet. In this case, it's not. It's just a lower bound. That's all. So far, that's all I've said. It's just a lower bound. In fact, here, let me tell you what the Lagrange dual function is for you right now. It is a lower bound on an optimization problem. Gives you a lower bound. It, of course, can give you, it's parameterized by lambda and nu, by these so-called dual variables. Now, in some cases, if you plug in some lambda and nu, you're going to get the following lower bound, minus infinity. It's a valid lower bound, totally uninformative. Okay? But it's always a lower bound. In some cases, you plug in lambda and nu, and you're going to get actually an interesting lower bound. And this, that's not obvious. So right now, you should just think of it as a lower bound. Lower bounds can be good. They can be tight. They can be crappy. We're going to get to all that later. Okay. I just want to tie together the idea of the conjugate function and Lagrange duality. So if you have a function with just linear inequality and equality constraints, a problem, and you work out what the dual function is, it's minimum of f0 plus, I collect this together, and multiply by x, and then that's, of course, a constant. Okay? And what this means is the following. If I focus on this, and then go and look up what the conjugate function is, which was the sup over x of y transpose x minus, what was it, something, minus f of x. That's the dual. If you plug in also all the right minuses, you get this. It's equal to that. Now, what that means is the dual of, the Lagrange dual function of this thing is exactly equal to this. It's equal to that, just period. Okay? Now recall, actually when we calculated a couple of conjugate functions, actually recall the conjugate functions often have domains that are not everything. I think you did the max function, and the conjugate function turned out to have a very small, it was actually the probability simplex was the domain of it. So that'll automatically impose some equality constraints in here when that happens. But here's an example. The maximum entropy problem is maximize sum minus xi log xi subject to some inequalities and equalities. And by the way, that's already a really interesting problem because it says lots of things. It says basically find me the maximum entropy distribution that has these expected values. These are just known expected values. These could be moments, could be probabilities, it could be anything. And these are inequalities on expected values. So it's really quite a sophisticated problem to ask. What's the maximum entropy distribution, for example, on these points that, for example, has the following mean, the following variance, the following, kurtosis or whatever it is, something like this, has the probability in the left tail less than that. And, you can go on and on, make a very sophisticated thing. That's the maximum entropy problem. That's this thing. And if you work out what that is, when fi of x is the negative entropy here, that's minimized negative entropy, you will actually get the sum of exponentials. So the dual function for a maximum entropy problem is going to involve a sum of exponentials. Now, if you're in statistics, and I said statistics, not probability, this will be very familiar to you because it has to do, it's a connection between exponential families and maximum entropy. And we'll see more of this later. But just a hint. Okay, now we get to the dual problem, and to write down the dual problem, it's the dumbest thing ever. If someone walks up to you and says, I have a bound on a problem. I have a lower bound on my problem, right? But it's parameterized by this vector lambda and this vector nu. And then you say, well, that's interesting. The only thing interesting about a lower bound is, well, that it's a lower bound. And if someone has multiple lower bounds, obviously the higher the lower bound, the more interesting it is. So you could just say, all right, what is the best lower bound on the original problem you could establish by Lagrange duality? What is the best lower bound? We don't know if it's sharp. We're just saying what's the best one. And it kind of wouldn't make any sense to really examine any other anyway. All right. That leads you to just this problem right here. Now I want to point something out. This is always a convex optimization problem, no matter what the primal problem was. Oh, by the way, this is called the Lagrange dual. Sometimes it's just shortened to the dual problem here. In fact, people say the dual problem the same way we say the optimal point, even in situations where we don't know, in fact, that there's an optimal point. We're actually going to see this multiple duals the way the word is used on the street. There are lots of duals, but we'll get it. For now, it really is the Lagrange dual problem. And it says simply maximize the dual function subject to this, period. Just subject to the lambdas being positive, that's all. Okay, now often what happens is g is minus infinity for some values of lambda and nu. We've already seen that a couple of times. That is a not interesting lower bound. And it sure is not going to help you maximize something. To find a point where this is minus infinity, you know, well, I mean, this thing could be minus infinity. That can happen. But the point is it's not an interesting value. So in fact, often what happens is you pull the implicit constraints in G out and make them explicit. Okay? Now, here, for example, let's go back and look at this. The dual function for this LP is this weird thing that looks like this. I drew it somewhere. There, it was this sick thing here where, you know, this thing is kind of going up on a line, but off that line, the thing falls off to minus infinity. And we're simply to maximize that subject to lambda positive. However, it's easier to simply take the implicit constraint out, and you end up with something that looks like this. Okay? So here, here's the so-called standard form LP. And then this is what it looks like when you have actually pulled out this implicit constraint. Technically speaking, this is not the Lagrange dual of that. Okay? However, people would call this the Lagrange dual. So you're given a little bit of license to form the Lagrange dual and do a little bit of trivial rearrangement, and people would still call it the dual or something like that. Technically speaking, if you're deposed, if you're under oath or something like that, you would say, nope, that is not the Lagrange dual of that. This is a very simple transformation. This is equivalent under a very, very simple equivalence to the Lagrange dual of this. The Lagrange dual of this thing is that, where g is this sick function. So I just want to point this out. Okay, and by the way, let's see what happens here. That is also an LP. And let's see what it says. Here, I can say something about this problem. If you have a feasible nu here, then minus b transpose nu is a lower bound on the optimal value of this problem, period. This thing says, okay, you have a family of lower bounds. Please get for me the best lower bound. That's what the meaning of this problem is. By the way, we'll also see this has beautiful interpretations in a lot of cases. So for example, in engineering design, it will make a lot of sense. X will be a suboptimal design, for example. I mean, any X here, if it's feasible, it satisfies the constraints. But if you'll maintain it's something that's feasible here would be a suboptimal design. Okay? The nu will have a beautiful interpretation. It's a dual feasible nu in that case is a certificate on a limit of performance. That's what it is. That's the meaning of nu here. Okay? Actually, we'll see that when you look at a real problem, it will have physical significance. We'll get to lots of examples. But abstractly, it's a limit of performance. Now, by the way, if you're doing engineering, you may not care about this. If you've been working all day and somebody comes along and says, how are you doing on designing that thing? And you go, I have got an excellent lower bound. This is not generally what you do engineering for. Oh, by the way, there is some engineering where that's really what you want to do. If this is a question of how bad could something be, if let's say you're at a bank and they want to know, okay, how much trouble are we in? What's the worst thing that could possibly happen? Then a lower bound actually gets interesting, right? So then it's actually, and of course in this plus of n, but that's the idea. Yeah?
Could you please say why that was not technically the Lagrange dual on the right?
This?
Yes.
Sure, that's the Lagrange dual. That's why.
I mean, relative to the LP.
No, they're not the same thing. I mean, they're not the same thing. This is minimizing a function, which is a weird function. It's equal to, minus b transpose nu, provided that a transpose nu plus c minus lambda equals 0. Okay, something like that. And it's minus infinity otherwise. Okay, so that's what this is. So, and by the way, if you were very careful, it would make a difference. Let me explain that. Okay, over here, if the question would be over here, what happens if operationally it makes a difference? I mean, slightly. It's kind of silly, but here it is. Suppose I throw in a nu for which A transpose nu plus C is not a non-negative vector. Okay? Then this, in this problem, when I say, how about this nu? How do you like that? What is sent back to me is actually something, is the infeasible token is sent back to me, saying your nu is infeasible. Okay? Over here, it's actually more interesting. Over here, if I throw such a nu in or whatever, here, what comes back to me is, what will happen is no problem. What happens is the objective function sends me an OOD token out of domain. Now, it's a concave function. That means it's minus infinity. So either way, so you get basically two slightly different exceptions are thrown in this thing. But I want to point out that these are just, you can call this just silly semantics and all that if you like, but it's very important to understand these are not the same problem. So, okay. I mean, by the way, this is, don't focus on these minor things. That's something you can think about. You can read this, think about it on your own. And don't let silly little technical things get in the way of what the big picture is. Big picture is you have an optimization problem and you form another one called the Lagrange dual, period. That Lagrange dual problem essentially is saying what is the best lower bound on the optimal value of the first one I can get using the Lagrange dual function. That is what's important. Okay? So now we get to the idea of weak and strong duality. Now, weak duality says that D star is less than P star. Now here, let me say how this works. Okay. So D star, so in this context, this is called the primal problem, or the original problem is called the primal problem, and the Lagrange dual is then called the dual problem. Okay, so that's the primal and the dual, and we'll call we've already assigned the symbol P star to mean the optimal value here. We're going to let D star be the optimal value of the dual problem. Okay, so optimal value of this is going to be denoted D star. You always have D star is less than P star. Why? Any dual feasible point is a lower bound on P star, so the best one is also a lower bound. So you have this is called weak duality. It's called weak duality because, let me review what mathematics, the deep mathematics required in establishing this, right? It hinged on properties such as the product of two positive numbers is positive and the sum of positive numbers. So it's weak because you can explain it to somebody in junior high school. I mean, they might not have taken those 14 steps, but the point is there's nothing in them that's hard. So it's called weak. Okay? All right, that's weak duality. All right, it always holds. Convex, non-convex, it's absolutely universal. It could be stupid. You could indeed have D star equals minus infinity, in which case your best lower bound is of no interest whatsoever. Okay? That can happen. But this is always true. Okay. Now, if we go to the partitioning problem and we ask, what is the best lower bound on the two-way partitioning problem you can get from the Lagrange dual, you will form this problem. That is a semi-definite program. And now things are interesting because although this is something that was not known 15 years ago and absolutely inconceivable 20 years ago, I can tell you this. This SDP, you can solve it. People can solve it. You can solve it like that for 1,000 variables. Just no problem here. And if you knew what you're doing, you could go easily to problems with 10,000 and 100,000. Of course, W has to be sparse there. That means, by the way, in your group of people you're partitioning, a lot of them don't have opinions about the others. That's what it would mean for W to be sparse. So there'd be a big matrix, a lot of zeros. You'd see some large plus ones. That's people who hate each other. And you see some negative ones. Those people who like each other. And then you have to partition. But that's a sparse W. Anyway, I'm getting off topic here. So the point is you can solve this SDP and you will get a lower bound on the two-way partitioning problem. That is fantastically useful if you couple that with a heuristic for partitioning. So you do some crazy heuristic. There's lots of heuristics. Some of them work really well, by the way. Now, you don't expect it to work all the time because you are solving, after all, an NP-hard problem in general. So you don't expect it to work well all the time. But what happens is you'll do a partition. and you'll say, here's my partition, and here's the number I got. It'll, whatever it is, it's the X transpose WX. That's it. And you want to know, could there be a better one? You can solve this SDP, and in fact, you'll see a lot of times the numbers are pretty close. At least it's a good thing to know. You would know, I have a partition, but there's no partition that's more than, I'm at most such and such suboptimal, period. And you might just say, okay, that's good enough. All right. Okay. Strong duality, this will not rely on element, whatever, junior high math, okay? Strong duality is going to be that lower bound is tight. That says there's a lower bound that goes all the way up to the optimal value. That's strong duality. And that's not, you can't, we'll see what it's equivalent to, but that is not trivial. And by the way, it often doesn't happen. Okay, so in two-way partitioning problem, by the way, if it were true there, then you'd have P equals NP, because this problem we can solve in polynomial time. And so if in fact P were equal to P star were equal to D star something, and in fact there's even approximation. If you know about computational, if you know about complexity, and you have problems. So if you have something that's not even approximable or something like that, then that tells you that P star basic, you can't even get something where you can bound the gap or something like that. But I won't go into that. Now, here's an interesting part. When a problem is convex, you usually have strong duality. Okay, so that's actually amazing. It's going to have a lot of implications. It's going to be equivalent to, by the way, something. It's going to involve the separating hyperplane something. We'll see what it connects to. It's going to have a lot of implications. The fact that strong duality holds usually for convex problems. Now, there's a whole their entire books, multiple courses. Not here, but at some other schools. You could take entire courses, read books, thousands of papers that elaborates on this one word, usually. Okay? Now, and basically these are called constraint qualifications. So a constraint qualification theorem goes like this. It says if the problem is convex, if the primal problem is convex, and then you insert your constraint qualification here, okay, then P star equals D star. That's a constraint qualification. You could read, you could devote your life to this. On occasion, these issues actually do come up, but maybe less frequently in applications than the people who devote their lives to it would like to think. I'm saying that, of course, because their grad students will watch this and then alert them to it. So just making trouble, sorry. Okay. These are called constraint qualifications. Now, by the way, if you're in this industry, sub-industry of constraint qualifications, then this is like the sledgehammer, the most unsophisticated one there could possibly be. This is like the basic one that everybody knows. Okay, this is the least squares or something like that of the constraint qualification world. It's Slater's constraint qualification. Although, actually, I should look into this sometime. Anyway, I think it's for sure the correct name here would probably be Russian, but we won't get into that. No, almost no doubt. In fact, I even know who to ask. I should switch it. That would even cause more trouble. I should do that, actually. Okay. So let's call it Slater's constraint qualification. And it says this. It says if you have a convex problem like this, it says if, I'll say it, I'll make this simple case. If there is a strictly feasible point, if there exists one, then P star equals D star. And strictly feasible means not just that you meet the inequality constraints, but you do so with positive margin for each one. That's the condition. Okay? Now, I should add that basically, it's completely clear that for most problems, that covers everything in engineering, pretty much. I mean, as much as people would make fun of Slater constraint and give you, reasons, and they could make examples up why it's not sophisticated enough. And sure enough, there are problems where you don't have a strictly feasible point. But for most problems that come up in engineering, certainly anything in like machine learning, probably almost pretty much anything, you're going to have, this makes perfect sense, right? Because, for example, if the third inequality was like a limit on power, right? It doesn't make any sense to say, you know, and it says that the power of some circuit has to be less than 100 milliwatts. It's sort of like, I mean, just think about it, right? So if Slater's condition failed to hold, it means there exists a circuit that dissipates 100 milliwatts. But there's no circuit that dissipates 99.9999. Because if there were, Slater's condition would hold. Everybody see what I'm saying here? Right? So, and the answer to that is like, who cares? You know, there's one that's 100, fine. The spec is now officially 100.001. Doesn't make any difference. Everybody, that's totally obvious. Now Slater's condition holds. Right. So I think this is my general argument, that it really doesn't make a whole lot of sense to worry too much about this. In machine learning, if you look at this and someone says, yeah, what about Slater's? I took a whole quarter on constraint qualifications. What if, you know, what if Slater's constraint what if you're doing something, this is a support vector machine or something like that, then you look at the person and you go, excuse me, where did the data in the problem come from? The answer, it came from a bunch of like data, like, you know, spam filters and features and things like that. The data is all, who knows about the data? Who knows where the data came from, right? And certainly all the data could be wiggled a little bit and the stupid thing should still work. If solving that problem relied on these most fantastically subtle facts as to whether strict inequalities held or weak inequalities, and one but not the other held, then I got news for you. You're not doing engineering, you're not doing statistics, you're not doing economics, you're doing something like pure analysis. Okay, so that's my little story on it. Again, there are actually cases where these come up in practice, but they're pretty rare. And mostly I'm saying this to irritate people at other universities, my colleagues, who will be alerted to this, watch this tape, and be very angry. So that's okay. But I thought I'd mention this. Okay. All right. So let's go to the inequality form linear program. Here you want to minimize C transpose X subject to AX less than B. We already worked out well, we can work out, no, we didn't do this one, but we can work it out. It's easy enough. G of lambda is C transpose X plus lambda transpose times AX minus B, because I put the B on the left-hand side to make this F less than 0. I do this, and I infimize this, but we know how to infimize a affine function. You get minus infinity unless the linear part vanishes. So I get this. And so this is the dual problem. Notice this is actually not the dual problem. So if there's lawyers present, you would say this is a problem that is trivially equivalent to the dual problem. Okay? But, you know, after a while, if there are no lawyers present, you just say that's the dual problem or something like that. So that's it. Okay. Now, Slater's condition says that if the feasible set, of course the feasible set here is a polyhedron, and by the way, one possibility is the feasible set could be empty, which is in fact a polyhedron. This says if, what Slater's condition says geometrically is very simple. It says if that polyhedron has non-empty interior. That's what this means. It means basically there's an interior point. Okay. If it has non-empty interior, then you have strong duality. So you have P star equals D star. Okay? So that's the picture. Now, in fact, for an LP, you can say much more. It turns out for an LP, you always have strong duality except for one sick case. And that's when both the primal and the dual are infeasible. And by the way, you get quite a gap between P star and D star then, because P star is plus infinity and D star is minus infinity. But anyway, let's look at a quadratic program. Let's minimize X transpose PX subject to AX less than B. That's minimize a quadratic form over a polyhedron. The dual function is this X transpose PX. And we're going to assume P is positive definite. Actually, that's so that I can avoid the horrible way to write down. It's not that big a deal, but the horrible way to write down, to infimize a general quadratic function with a linear term, because I don't feel like doing it. So this will work, though. So here, the Lagrange dual is, well, the dual function is you infimize over X transpose PX plus lambda transpose AX minus B, here, like that. And now I minimize over X. Now the nice part is P is positive definite, so I know how to minimize this. It's P inverse times whatever, something. I'm not even going to do it, because it's easy to minimize strictly convex quadratic function. So I minimize it. I plug that x back in here, and I get this thing, okay, which is I get minus 1/4 lambda transpose A, P inverse A transpose lambda, or something or other. And my dual problem then looks like this, like that. Oh, by the way, this really is the dual problem. Because in this problem up here, notice that the dual function, the domain is all of R, let's call it Rm. It's all of Rm. Okay? So in this case, the dual function is domain is everything, which is to say you get a lower bound for any value. You plug in, you take random numbers lambda, and you're not going to get a trivial lower bound. Okay? I mean, you might get a rather stupid one. For example, you might get the lower bound minus 7. Anybody want? Let's talk about the lower bound minus 7 here. Why is the lower bound minus 7 valid for this problem? Because the objective is always non-negative. Okay, so, but the point is you get a lower bound. All right, and you get this. So that's the dual problem. And by the way, what we're saying here is not obvious at all. What we're doing is we're saying you want to solve this quadratic program. We haven't yet told you how to do it or how it's done or anything like that, but we'll tell you this. If you come up with any vector lambda that's non-negative, and you evaluate this concave quadratic function, you get a lower bound on the optimal value of this thing. This has lots of uses. For example, suppose someone says, I know how to solve this problem. And you say, how did you do it? And they go, are you joking? Well, that's like IP. If I told you, I'd have to kill you. My new method. I'm patenting it right now in Kazakhstan. Okay? I can't tell you how I did it. And you say, well, why should I believe that that's the optimal x? How do you prove it? You say, well, watch this. You say, check out this lambda. Notice that it's bigger than or equal to 0. And you go, yeah. Then you evaluate that number. And that number is equal to the value up here of the point. That, by the way, ends the discussion. That x is feasible. And by the way, you would call that lambda a certificate proving it. Everybody got this? And notice that you didn't have to say how you did it. Everyone got this? And then you'd say, hey, how'd you get the lambda? And you go, like, I'm going to tell you that either? That's my patent application number 2. Okay? But the point is, you can do this without, the lower bound actually has a value independent of where it came from or something like that. So you have this idea that you can certify the solution. Okay? Without revealing, actually, how you solved the problem originally, A, or B, for that matter, how you came up with the certificate. So we'll get to these ideas later. Now, Slater's condition says the following. If this polyhedron has non-empty interior, then these are absolutely equal. Then there always exists a certificate proving optimality of the optimal x, period. Always. So, okay. Now, by the way, a very small number of non-convex problems have strong duality. I'm not going to go into it because it's complicated and so on. This is actually covered in an appendix of the book, and I would encourage you to read it. This one is not obvious. And actually, there's a whole string of these. You know, there's like 15 of them or something like that. And they're just weird things that have to do with specific problems that are non-convex and just happen for deeper reasons to have zero duality gap. Okay? The quadratic ones are the ones we collect at the end of the book in one of the appendices. There are others. You will see them. They're kind of weird, and some of them are quite strange. I mean, they might involve like weird. The one I've seen recently where it involves complex polynomials of degree 4, right? And then something that is highly non-convex, zero duality gap. And it comes down to something in algebraic geometry. But that's always the way these are. These are not simple. This is just to say there are non-convex problems with zero duality gap. A few. Okay. Let's look at the geometric interpretation. All right. So let's see if we can do this right. So we're going to do a problem with just one constraint. So what we're going to do is we're going to minimize. I'm going to write the graph of what I'm going to do is sort of the graph of the problem. What I'm going to do is for each feasible x, or each x in the domain, not feasible, each x in the domain, I'll evaluate this pair. So although the problem may be happening in 100 dimensions, for every x, I'm going to plot a point which is in this plane. And one basically, this tells you the objective value, and this tells you the constraint function. So basically, everything over here corresponds to feasible. Okay? And then the height corresponds to the objective value. So quite obviously, that's the optimal value of the problem. And any point that ends up being colored there is optimal. Okay? So that's clearly, that's the optimal value, P star. Everybody see that? So that's the idea. So these points, I mean, that point has got a very nice objective value, but it's infeasible because its constraint function is positive. Okay? So that's P star. Now let's see what the dual is. How do you get Lagrange duality in this picture? Well, Lagrange duality works like this. You minimize f0 plus lambda f1. Now, on this plane, that corresponds to taking something here like this, and it's got a slope of, is it 1 over lambda or something like this? It's, let's see, if that's u, it's slope minus lambda. So I take something like that. So for example, if you fix lambda and then ask me to evaluate the dual, what you do is this. You fix a slope here, and you march down this way until you just barely leave this set. And that would be right there. Okay? And then, when you work out what g of lambda is, it's this intersection here. Okay? So this is g of lambda. And now, the dual problem says optimize overall lambda. So if lambda is 0, you get this. You go down there, and g of 0 is this number right here, which is indeed a lower bound on P star. It has to be. Okay? Now I crank up the slope, and as I crank up the slope, g is rising. Okay? And it keeps rising until you just hit here, this point. At which point, here, it's right there. Okay? Now, as I keep increasing lambda, what happens is the optimal point actually is here, and this thing is rotating around. It's not a fixed point. It's rolling the contact, but because it's got sharp curvature, it's rolling just slightly. It's rolling along here, and as I increase lambda, g gets worse and worse. And in fact, if lambda is huge, it looks like this, and g is very negative. It's still a lower bound, just a crappy one. Everybody see this? So d star is that point. Okay? By the way, the difference between P star and D star is called the duality gap, or the optimal duality gap for that problem. Question?
How does the complexity of the dual and primal problem relate usually?
We're going to talk about that. But I mean, it depends very much so for example, in a non-convex primal, like in general two-way partitioning problems, NP hard. But the dual is an SDP. That's easy. So they could, in that case, they could be infinitely far away. Now, in the case of a convex problem, right, now it gets interesting. So in a convex problem, you will see later, they both solve the problem. And a lot of people get all excited. They go, oh, how cool, I can solve my problem by the dual. It turns out if you really know what you're doing, the complexity of the primal and dual are equal. If you really know what you're doing. You will in about 4 weeks. 3? I don't know, whatever it is. Yes?
How did you rule out the right bottom point for P star and just say it was that point?
How did I do it?
Yes.
Well, the first thing I asked is this shows you the objective and the constraint function for every possible point in the domain. Okay? Now, that point is not good. For one thing, it's got a high objective, but it's also infeasible. So feasibility, anybody who landed on the right here is infeasible. So in fact, these are all very interesting, but they're not relevant as far as the optimization problem is concerned. So we simply look at these. Now, every point that got shaded in here is feasible. Okay? The height tells you the objective value, and so you want the lowest point among these. That's clearly right there. And you go across here, that's P star.
Why was the right side infeasible?
Because your first coordinate here is your constraint function. And f1 has to be less than or equal to 0. That's what it means to be feasible. Okay? So that's the picture. So here you have a gap. By the way, this thing strongly suggests something very interesting. And you can see why convexity of the problem is going to come in. When f1 and f0 are convex, this weird set G, now what I'm about to say is actually not true, but it's close to true. That weird set G is convex. Okay? When something is convex, you have a gap here because this blob is non-convex. So if this thing had to be convex, you can't have a gap. Everybody see this? That's what's going to happen. Now I'll tell you the truth. G is actually not convex, but its lower left corner, which is what we care about, is. So now I corrected it and said the truth. But okay. Now you can also, by the way, see how Slater's condition works. So if you take not G but A, that's the set of points that sort of you can meet or beat in a bicriterion problem. So basically, this is what if you take A and then color in all these points here. You only care about the ones down here. This Pareto thing is the only optimal point here. And now you can see A will actually be convex if that's convex and that's convex. So A will have to look like this. Slater condition says that somewhere A goes a positive amount, or whatever you want to call it, it goes into the left side. Because otherwise you can get weird. I can show you what things with convex problems with positive duality gaps look like. They look like things where it looks like this, and then right as you get to this axis, it jumps up some amount. And you can easily construct a pathology. But these are the kind of things you would study in one of these whole courses on this topic. So that's the idea. And so you can even sort of get how Slater's condition holds on all this. Okay, I mean how it connects to all of this. Okay. I'm going to mention one more thing. We'll get to one more topic. It's complementary slackness. So let's assume that strong duality holds. And actually, I don't care if the problem is primal or feasible. Okay, convex. What I said made no sense whatsoever. Okay, so so what I meant to say was I don't care if the primal problem is convex. That's what I meant to say, but it just came out a weird permutation. Okay, so I don't care if the primal problem is convex. Of course, the dual problem always is convex, period. So I can care about it all I like, but it's not relevant. It's always convex. Okay, so let's suppose strong duality holds. And let's suppose x star is primal optimal and lambda star and nu star are dual optimal. That says this. That says, by the way, this is the case. I mean, this is basically what it comes down to. What it says is that x star is an optimal point. Lambda star and nu star you can think of then as a certificate establishing optimality of x star. Okay? Now, by the way, these ideas, we're going to use them from now on. They're going to come up computationally. All algorithms are going to work this way. All modern methods, they don't, you haven't done it yet, but whenever you solve a problem, it doesn't just say here's x and you have to trust the software or whatever. It doesn't work that way. Although you haven't seen it returned to you yet, all modern solvers, well, of the ones we're going to study in this class, they produce not just the solution, but they also return, no exceptions, a certificate proving that it's the solution. So you don't have to trust the implementation. Everybody see what I'm saying? So these are going to have this is just completely standard. It's going to be in everything. Or these ideas are going to they're going to diffuse through everything we do. Okay. So basically you think of that as an optimal point, optimal design, whatever you want to call it. This is a certificate proving that's optimal because that's a lower bound on P star. That's a point that's feasible and has objective value equal to this lower bound on P star. Therefore, it is P star, period. Okay. Now this thing, by definition, this thing is the infimum over all x of G here with these optimal Lagrange multipliers. Okay, but if it's the infimum over all x, it's certainly less than or equal to this when I plug in a particular x, and I'm going to choose to plug in x star. Okay, so I plug in x star, and I have the following. Very interesting. This says f0 of x star is less than or equal to f0 of x star plus something where every term in that is less than or equal to 0. Okay, and every term in that is 0. So this one is not relevant. Okay. Well, we'll get we'll get to that. Okay. Yeah. So everything here is 0. And now you say, now wait a minute here. If this thing is less than or equal to that thing is less than or equal to that, and that's the same as that, then they're all three equal. And we have no choice but to conclude that the sum of lambda I star times fi of x star is 0. Okay? But there's more than that. Wait a minute. This is a sum of numbers, all of which is less than or equal to 0. If you have a sum of numbers which are less than or equal to 0, and it's equal to 0, there's only one conclusion. Every single one of those numbers has to be 0. And that says the following. Lambda I star times fi of x star is actually equal to 0 for all of these. Okay? And that's known as complementary slackness. And what this means is the following. It says if you have any primal optimal point and any dual optimal point, the following must hold. If the inequality constraint is tight, I'll turn it around this way. If the inequality constraint is tight, you must have, I'll turn it around. If the optimal Lagrange multiplier is positive, it can only be positive or 0, then that thing has to be tight, period. If a constraint is loose at the optimal point, these Lagrange multipliers have to be 0. Okay? So that's going to be, this is going to tie into all, it's going to have lots of implications. It's also going to, when we give other interpretations of what all this means, it's all going to tie in, like with these things being prices, for example. But we'll quit here for today.
Just so that they don't apply to 0, right?